Clicking send or typing a URL triggers an invisible, highly structured negotiation before a single byte leaves your device. This negotiation happens at the application layer. It acts as the strict translation interface between the software you interact with and the underlying network that actually carries the messages. This TCP/IP model stack places the application layer at the top, housing specialized protocols that prepare user inputs for network transit. In the OSI model, this block is subdivided into 3 distinct functions: application, presentation, and session. In this presentation layer panel on the left, data is formatted, compressed, and encrypted for secure transit. Meanwhile, the session layer on the right handles the connection lifecycle. It establishes, maintains, and recovers the active dialogue between 2 applications. The protocols selected at this uppermost layer exercise architectural determinism. They dictate both the physical and logical structure of the entire network below them. Communication between diverse environments, like Linux and Windows, is only possible when both sides implement an identical application layer protocol. Successful communication requires the protocol implementation on both ends to be perfectly compatible. To understand how this works, we will analyze 3 structural choices that govern modern networks: how data is hosted, how it is secured, and how its state is managed. Network engineers define system architecture through the selection of Layer 7 protocols, dictating the fundamental behavior of data across the environment. The first architectural choice is how data resources are distributed and accessed across a topology. In the client-server model, roles are strictly assigned. A dedicated server holds resources, while the client requests them. Data flows are unidirectional. Clients initiate the exchange, pulling data down in a download or pushing data up in an upload across the network. Centralizing resources on a single server makes it easy to control user authentication and manage files from a single point of authority. But networks can also use the exact opposite architecture, the peer-to-peer or P2P model. As shown in this P2P topology, the central server is eliminated entirely. Every connected device, or peer, has direct access to shared files and hardware, like a printer, without going through a central hub. Notice the labels in this exchange. Both peer A and peer B are marked as client and server simultaneously. A single machine might act as a server to deliver a file for one transaction, while instantly acting as a client to request data in another. Decentralized applications often rely on foundational frameworks like the Gnutella protocol, which allows these peer devices to dynamically locate and share resources across the mesh. While P2P eliminates the single point of failure inherent to centralized servers, it increases the complexity of securing and administering the network. Choosing between client-server and P2P dictates where the burden of processing and security resides, either concentrated in a core database or distributed entirely across the edge of the network. When we look at web traffic, we hit a clear routing problem. Humans navigate using names, but routing hardware requires numeric IP addresses. The Domain Name System, or DNS, solves this. It acts as an automated directory service, mapping a fully qualified domain name like Cisco.com into an IPv4 record or an IPv6 AAA record. This sequence shows how DNS and transfer protocols load a web page. After a user types a URL, the browser queries a DNS server to resolve the domain into an IP address. Only then does it initiate an HTTP GET request to that specific numeric location. HTTP defines strict types of requests, detailed here. The browser uses GET to retrieve data like an HTML page. POST is used to submit form data, and PUT uploads resources directly to the server. But standard HTTP has a critical vulnerability. All headers and payloads travel in plaintext, meaning any node along the path can intercept and read the data. To fix this vulnerability, networks use HTTPS, wrapping the data stream in Transport Layer Security, or TLS. As outlined here, this provides 3 things: server authentication, data encryption, and integrity checks, securing the packets before they ever touch the physical network. The underlying HTTP request and response mechanics remain exactly the same. They are simply encapsulated within a secure TLS tunnel. Decoupling the DNS directory function from the HTTP data transfer creates a modular architecture. If a web server changes its IP address, DNS updates the record, and the change remains completely transparent to the end user. Web browsing operates on a real-time request and response cycle. Electronic mail requires a different architecture. This diagram illustrates email's store and forward design. Messages do not travel directly from host to host. Instead, they sit in databases on intermediary mail servers. As the key takeaway notes, clients never communicate directly. They strictly route through their respective ISP mail servers. Pushing that data requires the Simple Mail Transfer Protocol, or SMTP. It is the exclusive protocol used to send mail from a client to a server and from server to server across the internet. SMTP requires a specific header format containing sender and recipient addresses attached to a body payload, but its capability stops an outbound transmission. It only sends. To retrieve messages, network administrators must choose a second protocol, which forces a decision about how the state of the data is managed. POP3 downloads messages locally and deletes the server copy, meaning if the machine crashes, data is permanently lost. Alternatively, IMAP downloads a copy but securely retains the original on the server, dynamically synchronizing exact folder hierarchies between the server and the client. This creates true state synchronization. Deleting a message locally forces a synchronized deletion on the server, ensuring the state remains identical across all connected devices. Choosing between POP3 and IMAP is not a matter of software preference. It is a strict architectural decision about where the master record of data resides. The application layer functions as a diverse ecosystem of specialized translation protocols. Communication across this layer is governed by an absolute law. Endpoints must achieve perfect protocol parity before any exchange can occur. These protocols dictate the physical topology of the network, forcing the structural choice between centralized servers or distributed peer-to-peer meshes. They establish the security perimeter, delineating exposed plaintext HTTP from the encapsulated channels of HTTPS, and they govern data state and synchronization, as seen in the divergence of POP3 and IMAP. Mastering the application layer goes beyond memorizing acronyms. It requires understanding the underlying logic and the structural parameters that govern all modern digital communication.